All right, there's your Pi Day cartoon for you. You don't get it.
We can't even see that far.
You can't even see that far? How about that? That's better? Okay, now you get it. All right, here we go. Go. All right, I'm going to try to get that thing to go away because it's going to cover up stuff. Okay. I got 17. Oh, look at mine. All right. How'd you do? All right. Woohoo. Okay. So we're going to do synthesis problems using the Diels-Alder reaction. So what you kind of got to do is figure out which bonds are the two new bonds that, okay, to make the ring. All right. And then you figure out which side's going to be the diene and which side's going to be the dienophile. And remember that dienophiles like electron withdrawing groups. Name one electron withdrawing group.
Bromine.
All right. You didn't even say benzene. That was your fan answer on the NMRs. Okay, so we're going to make each compound below using a Diels-Alder reaction. So look at the first one on the left. Okay, so where do you see the new bonds as being? Where are the two new sigma bonds? What? Because we're going to put a line through them, basically. Okay, so where do you want me to put a line? Here? 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 All right. Okay, so what will the left side of that ring come from? The diene. Okay, there's your clue. Where are you? Yeah. And I'm going to write under here, diene. Okay, what is the right side? Where does that come from? A double bond, okay. With NO2s on each side. Okay. So notice that your mechanism is like this. Practice it 50 times. Okay? All right, now look at the next one. What do you think about that one? It's way more complicated looking. Where do you see the two new bonds as being? I think we need a little purple in our life today. Okay, so where do you see the two new bonds? Where am I going to put my little cuts? There's a lot of choices, way more. What do you think? Okay, and another thing that I should mention, the way this is drawn, do you see that this bond is in front of that bond? Okay, what my program does is it'll put a little space there, like automatically for you. Okay, all right, so where do you want to break it? Should I start pointing to bonds and you tell me? Does that work? Okay, how about this bond? This one. This one. Okay, this one. This one. This one. Y'all are doing good. All right, so what is the left side going to become? It's going to come from what of the two pieces? A what? A diene or, oh, I didn't write dienophile. I meant to. You already wrote it down probably. Okay, so what is the left side going to be from the diene? How do you know that? Because that's where the double bond is. Because remember, the double bond ends up between those two carbons in the diene. All right, so what am I going to do now? What should I draw besides the answer? Okay, here's a cyclopentane, and then what do I need? Okay, does everybody see that? Okay, what's the other piece? What do I have from this side? Okay. Everybody see that? Okay, so get another color. So we're going to go 1, 2, 3. Okay, your new bonds are formed between these two carbons and these two carbons. Those are the ones that we put the little squiggles through. Okay, I don't want you thinking those are oxygens, okay? It kind of looks that way. All right, how about this one? Oh, I got rid of this weirdness. I don't know what it's from. But when I got rid of it, then the thing crashed on. I forgot that was there. So is that on your side? On your no. Yeah. The squiggle, the little one. Okay, all right. So how are we going to break this one now? You should have 3 more compounds to do, right? Yeah. Okay. If you notice, there's a slide of 3, and then there's a slide of just 1. It's the repeat of those, so you have more room to write them. I took that other slide out. I decided it was redundant. Apparently, that was what I did that made the smart notebook software crash. All right. So what am I going to do? Where am I splitting it? Oh, let me tell you this. Y'all do it. Do it on your piece of paper, and we'll see how you're doing. Okay, see if you can get it. And then I'll do it and remove the white things, which are supposed to be covering. So you'll have a really nice copy. Notice that there's a diene and a dienophile every time. I didn't write that on the last one. Are these the bonds you broke? Okay. So your diene should look like that. Okay. You don't have that there because that is missing in your picture. Yeah, that's my bad. That was a my bad. I didn't even catch that. Okay, so put it in. Okay, and that's the dienophile. Okay, so if you had to draw the little mechanism, you could draw it, right? Yeah. Because we're like really good at that one. Like, please put that on the top. That's right. Okay. All right, how about this one? Is that the same one? Okay, yay. Do that one. Have 3 to go, 2 to go. Okay, so what ones did you break? Did you break this? Ooh, that was exciting. This one and this one?
Yeah.
Okay. Pretty funny. Did you get that? Did you forget this thing?
Yeah.
Yeah, I don't forget that thing. That one. Okay, now something about the nitros. Okay, here the nitros are on the same side. This is a cis double bond, right? All right, let me get so I can write. Cis double bond. Notice that they're both down over here. Okay, and they're both on the same side. What would you get if you did the exact same thing with this diene and this dienophile? Would you get the exact same compound? No, you wouldn't. You would have one of the NO2s would be up and the other one would be down. Okay, so let's see if we can't draw that. How you doing on drawing them? Have you tried yet? Ooh, probably makes you feel better if mine looks goofy. All right, there's that methyl group since we were trying to keep it the same. Okay, and then I'm going to have one up and one down. So whatever the configuration is of the nitros or whatever the groups are in the starting material, it will be the same in your product. So down here will be an H and up here would be an H. And it's just really hard to draw that well on the smartphone. Okay. All right, how about this one? A little twist in this one. What's the twist? There's 2 double bonds, so that means you have to have a triple bond in your dienophile. All right, so give that a go and see what you get. See, these are kind of fun. Isn't it Diels-Alder open cool? And it was a short class. When we cracked the cyclopentadiene, it was dicyclopentadiene. It was not short. Have a little fire kind of, you know, thing. When you did that Diels-Alder lab, did you see the thing glow with the UV light? Okay. And then after you were done, did you do a melting point and then go check it and it glowed again? Did you figure out what happened when you did the melting point? You didn't do that part? Oh, that's the cool part, because what happens is in the melting point capillary, you do a retro Diels-Alder and it goes back to the starting material, and that's how it comes close. Pretty cool. You were just glad to be done? Is that what you're telling me?
Yeah.
All right, so what'd you get? What was your dienophile? What?
Triple bond with the
Okay, I'll squeeze it in there. Okay, and what was your diene? Anybody know how to draw it? It's a 5-membered ring with an O. We're not going to worry about the naming. Oops. And Messed it up. I was just drawing what was up there. Let's see if I can't fix it. I wouldn't bet on it. That's actually not too bad. Okay, so you should get, I've gotten this one and this one. So which bonds did we break this time? Okay, we broke this one and this one. What's the difference? If you break the other side, notice where the CN is. CN is one of those electron withdrawing groups. Remember that dienophiles like electron withdrawing groups. So when you have two double bonds like that, you're going to have to decide, is it on the left or the right? Because am I always going to draw it so that you break it on? No. So to make sure you look at it both ways.
Why is there not a trouble?
On this?
Yeah.
It's there. I just didn't draw it in. You don't have, we don't draw it in all the time. Just like nitro, we write NO2, we don't draw what it looks like. I just drew it in over here for you. Okay? Everybody get it? Okay, good. Okay, now we're going to take this compound and we're going to add HX to it. Okay? This compound is a diene, right? And it's a conjugated diene. Agree? Double, single, double. Okay? So what happens when we do the reaction? Well, we're going to add, well, what does HX do? Make it big. What kind of compounds are HXs? HBr, HCl. They are acids. Okay, so what are they going to do when you have one double bond? Do you know how to add HX to a double bond? One carbon gets the H and one gets the X. And what is the first step? You add the proton. Okay, you protonate. So we're going to protonate this. Okay, so what do we have now? Okay, so where do you want to put the H? Do you want to put it here or do you want to put You want to put it on the top? Okay, remember first of all that there is one H there already, so I'll draw them both in. Okay, so what kind of carbocation did we get? Tertiary. What if we put it on the other spot? What if it looks like this? All right, hang on. I'm going to put it here. There's still an H up here, so I'll draw it in again because you guys like to forget about those. Okay, now where's the plus? It's up here. Is it just secondary? What is it if you're next to a double bond? Allylic. What's special about allylic carbocations? There, yeah. By what? Resonance. So you remember this? Okay. So what's the resonance form for this? We're going to take the electrons in this double bond and we're going to push it up here. Remember, there is an H here. Okay. So what do we get? Let's see if I can make it fit on here. Okay, here's that H, here's that H, here's that H, but this doesn't have an H. It is now plus. Okay, when you look at all of those resonance, all of those cations, who's the most stable? Which one do you think is the most stable? This one's tertiary. This one's allylic. What's this one? Tertiary and allylic. right? Because it's next to this double bond up here. I can write maybe. Okay, so and then what happens? What else did we make when we protonated? We made X minus, and then what is it going to do? It's going to add to the carbocations. Okay, so our possible products are going to look like this and this. My plus is in a bad spot apparently. Okay, because X minus goes to the plus. Let's see if I can't get that to, okay. So the proton adds to the end of the diene system. Note that the carbocation form is allylic, so it will have another resonance. And that's how you get two products. Okay, now let's look at one, I think, that has.
Yeah. There's
What are you writing?
the box.
The box? I don't know, I just restated what I did. Okay, now on the next page is the resonance form that I did on this slide, but I'll write it out again for you.
So is the X on the tertiary, is that the
Yes.
major product?
You'll see, just leave that be. Just leave that be right now. Okay. Sometimes you can't tell too. This is a weird one. I mean, I would pick that because this is tertiary and allylic. I think nature. But what about when there's not those carbons? All right, are you ready for me now? Okay, so these are the resonance forms for that carbocation. So we took the, ooh, I didn't lock every one of these in place. Okay, so then you also had X minus, and we're going to add to there, and an X minus will add to there. Okay, so this product is going to look like this. Okay, and this product is going to look like this. Okay, those are your two products. This is what you get from this edition. Okay, now I'm going to circle the carbons in the original diene system. Okay, 1, 2, 3, 4. Okay, I'm going to do that over here too. 1, 2, 3, 4. Okay, those are the 4 carbons. This addition is called direct addition. Or 1, 2 addition. This one is called conjugate addition. You only get it because it's conjugated, I guess. Conjugate addition. Or the other term that's used is 1, 4 addition. The 1, 2 and the 1, 4 have to do with the carbons of the original diene system. Is not related directly to nomenclature. Okay, because if you named that compound that we started with, you wouldn't use a 1, okay? So it has to do with those 4 carbons that I circled that are in the original diene system. So when you look at stuff in your book and stuff like that, it's going to talk about 1, 2 addition and 1, 4 addition, direct addition and conjugate addition. I think because 1, 2, and 1, 4 confused a lot of people, they kind of went to the terms direct and conjugate, but you'll still see that. I see it all the time. Okay, both of them. All right, so here is one. We have a very simple diene system, and we're going to add HBr to it. Okay, so what do you think are the products? So I'm giving. So what will happen first, we will do that, okay? Protonate the diene system. What intermediate am I going to get from this? CH2 double bond CH, CH, CH2. So I'm going to add hydrogen here, and I'm going to get this allylic carbocation. Okay, and then I also made bromide, right? Bromide adds to that. What do I get? Okay. What else can that carbocation do besides have bromine add to it? It can do resonance, right? Okay, so if you do resonance on this, you're going to get the double bond moved over, okay? And bromide will then add to that allylic carbocation. So what's your product, the second product? It's going to be Br, CH2, CH double bond, CH, CH3. Okay? One of those is the 1,2 product, and one of them is the 1,4 product. Which is which? What's the first one? 1,2. This is the 1,2 product, also called direct. This one is the 1,4 product, also called conjugate. Do you see how they're getting the 1,2 and the 1,4? It's which two carbons did the H and the Br add to? Did it add to 1 and 2? Or did it add to 1 and 4? Notice there is no such thing as 1, 3. Doesn't happen. Okay? Now, which one is major depends on the temperature that you run the reaction at. Okay? One of those products you might pick as being more stable. Which one would you pick as being the more stable product? 1,2 or 1,4? 1,4. Why? Because the double bond is more highly substituted, okay? Here the double bond substitution is 1. Here the double bond substitution is 2. Remember that from way back when we made double bonds, okay? Oh, that's my little video. Okay, I'll finish talking. When you look at this, this one is referred to as the kinetic product. I may have this on another slide. And this one is referred to as the thermodynamic product. Thermodynamic is more stable. Kinetic is formed faster. Okay, so y'all know what kinetics and thermodynamics are, right, from general chemistry. Okay, you probably did more kinetics, same thing. Thermodynamics, probably calculate those delta H's. Yeah, enthalpy, heat content. Don't worry, we ain't gonna do that. Okay, so thermodynamic is more stable. Kinetic is formed faster. Sometimes it is the same one. Okay, it isn't always going to be so obviously different like this one. But they've actually done this reaction at cold temperatures, like cool it down. And the major product is the one on the left. When they do it at higher temperatures, the major product is the one on the right. Okay, they've even taken this compound, okay, the direct addition product compound, and they heated it up, and guess what it does? It rearranges itself to the one. Okay, where the bromide comes off, you get the allylic carbocation, and then the bromine comes back. Yeah, kind of interesting. Somebody did that little study. It was not me. Okay, now here is the diene, and we're going to add HCl to it. Okay, we're going to add HCl. I decided we should do the video sooner. All right, so I have to go and get there. Hopefully everything is still recording. Oh, it's on the, gotta get off of that. I like how some things work and some things don't work. All right, so there it is. There's our little video. Okay. Okay, so do you see the pi orbitals there? Top and the bottom. Okay, now watch how it works. There we go. Go away, you little thing. It's like covering it up. Can I move it? There. We'll do it again. Okay, so the first thing that's going to happen is we're going to protonate. Oh, this is the Diels-Alder. Did I hit the wrong one? Oh, I did. I got up. There we go. All right, what's this one? This is it. All right, let me get this moved down. They have the molecules low. Okay, see how we're protonating? And then there comes the chloride in this example. All right, I'm going to try this. Why? Does it help if I make it bigger? Didn't make it bigger. I love it when I do these things. All right. Now it's big. All right, so we're protonating, making the allylic carbocation. That's right there. And then the chloride comes in. That's direct. Okay, now what's the difference between direct and conjugate? What's going to happen? The double bond is going to move, right? All right, so let's see if I can get that one to show right. Here is the double bond. There, I'm going to do this. One shot. Okay, so we protonated it, and now see how the double bond is formed in the middle. Okay, now remember that when you have two resonance forms, that the overall picture is what it really looks like. Okay, so do you need to see that one more time, or are you good? All right, let's try escape. All right, so let me go back here. Hopefully this will all be on there. My gosh. Okay, here's the conjugate addition, what we made. Okay, so remember that this is going to be, ooh, I did that thing again. Sigh. Okay. So we're going to get that carbocation. That's going to rearrange or have resonance with this carbocation. Okay, remember that the overall picture shows you exactly 2, 3, 4. Okay, this bond sometimes is double and sometimes is single. This bond over here in the middle is double or single. So what's going to happen is that negativeness is going to be shared amongst those 3 carbons. And where is the partial positives? We're going to have it here and here. You see it's not on that right carbon. Okay, so your halide is going to have the choice of coming in on this one or that one. Okay, that makes sense? Is it all that's, I know that was a while ago, wasn't it? Oh my gosh. Okay, why aren't I going anywhere? Okay, so here is, this is the major product at minus 80 degrees C. It's formed faster. That is the kinetic product. This one is the major product when it's warmed up, more stable. This is the thermodynamic product. I got it in there, sort of. Okay, and these are your 2 resonance forms. That's for the HBr one. Okay. Kinetic control, the major product is the one formed fastest. Thermodynamic control, the major product is the one that is the most stable. Remember, it can be the same one. It depends on your structure. Okay? It depends on the structures of the compound. Okay. Did you have to fill that in? Yeah, not very much. Okay. Okay. How does HX add to a conjugated diene? Is it open? Oh, yeah, you're all up there. Okay. All right. It's both 1, 2, and 1, 4. So when you have a conjugated diene on the test, on the reaction page, you all don't like that page. You know it's coming. Every test. I even give you a choice. Most of you didn't do the Fisher esterification that I thought you'd know real well because you didn't plan. Okay, you're going to have a 1, 2 product and a 1. So you can get 2 products. Okay, well, let me get that out of the way. Okay, what would be the best dienophile to use to synthesize the compound below using a Diels-Alder reaction? What would be the best dienophile to use? My watch was taking my heart rate. Two more exciting numbers. All right, now I have 18. Yep, it's B. Yay! Okay, we're going to break it here and here. Okay, what would be the diene? The one with the 2 methyls that was supposed to be in the other one. Okay, why break it there and not here? Why isn't it C? Yeah, why isn't it C? Because you want the dienophile to have the electron withdrawing. So that makes the reaction work better. Okay, why isn't it A? Because you got to have a triple bond. Why isn't it D? Because you got to have a triple bond. Okay, how do you know you got to have a triple bond? There's 2 double bonds. Okay, that's pretty much your clue. Okay, what would be the best diene to make the compound below? Now, if you don't all get it right, I might cry. Trying to give you some points before the break. I am gonna cry. We're breaking it here and here. So this side becomes the diene side, and this side becomes the dienophile side. We did the dienophile in the last slide, right? Okay. Yeah, well, we'll start it. Okay, so molecular orbital theory involves the orbitals from your different atoms, okay, all put together to make big orbitals for the whole molecule. That's why it's called molecular orbital. Okay, if you take inorganic, you might do some of this in there as well. Did I take inorganic yet? Are you doing that? No, maybe he does it in. Are you an inorganic 1 or inorganic 2? 1. Maybe he does it in inorganic 2. Because I thought Dr. Moe used to do. Okay. He does way more of it than I do. All right. So what we're going to do is we're going to look at ethylene. Okay. And the only thing that we're going to do is we're going to worry about pi. Okay. So remember that ethylene. Ugh. Get black. Ethylene is CH2 double bond CH2. Okay? CH2 double bond CH2. Okay? And there is 1 pi bond in ethylene. Agree? Everybody agree with that? 1 pi bond in ethylene. Okay? The other bond that's between those 2 carbons is what kind of bond? Sigma. Okay. Each one of those carbons in ethylene is what hybridization? I love it when I ask you these questions and you get all really quiet. sp2. Okay, both of them are sp2. Okay, so each one of them have on them a p orbital. What we're going to use in our pictures are going to be p orbitals. Okay, so you have 2 p orbitals. Blue and green are the colors used from this book. Okay. You can use any color you want, any 2 colors. There's no reason or rhyme for blue and green, except it was pretty, I guess. Okay, you can also use shaded and unshaded, okay, which might be easier if you only have 1 color with which to take notes, okay? I would recommend that you would color in one side or the other, okay? Every time that you have a p orbital, you have a top and bottom. Okay, agree? You have a top and bottom load. You have 2 parts to that p orbital. Okay, the difference between the 2 parts is going to be, one is going to be the inverse of the other. That's all it is. We used to, years ago, write plus and minus in the lobes. Back when I learned it, we wrote plus and minus in. But that made people think of positive and negative, and that really does not fit. Okay, so that's how come we went to this. Okay, you take your 2 p orbitals, and now we're going to put them together. Molecular orbital theory takes into account the possibilities. They can be the same, or they can be opposite. If we are in the same phase, we will make a bond, and that's what this is here. This is a bond, which is what you're used to. What is that line in between? That's just the sigma bond. We're not going to worry about. We're only going to worry about the p electrons, the p lobes. So they can come together and be matched, okay? Or they can come together and they can be unmatched. That's the other possibility. This area in between here is not a bonding interaction. Here we're bonding. When the lobes match, it's a bonding interaction. When they don't match, it's called an anti-bonding interaction, okay? And that area in between is referred to as a node. That's what that is. Well, there's blue lines up here and they're so light, I feel like, can you see them at all? I'll write over them, okay? All right, so we made two things. Now, we had two p orbitals. Notice how many molecular orbitals we got out. 2. You put in 4, guess how many molecular orbitals you're going to get? 4. It matches, okay? The bonding orbital is lower in energy than the anti-bonding orbital, which is why it is written down here, okay? Because it's lower in energy, okay? Just like when you do your regular atomic orbitals, only 2 electrons will go into a molecular orbit. We're worrying about, remember, the pi electrons, those 2. Okay, so one will spin one will spin the other. Okay, what happens is these things can be named different ways. Okay, one way uses the big size. Okay, this is the Greek letter psi, psi. Okay, the other way is to use the little pi's, and this would be pi 1, and this would be pi 2. I like the pi system better because they put a star there. The star stands for anti-bond. Okay, so why do we even go to all this trouble? Well, they found that this whole mode of theory helps to explain why certain reactions are, okay, and explains the stereochemistry that you get in the end. So whether you use psi's or pi's, it kind of rhymes. I think pi is good for pi day. We just got pi day. But if you gave this molecule energy, for example, UV energy, one of those electrons is going to jump. And where does it jump? It jumps into an anti-bonding. And then it will fall back down. And that's how you're going to get a UV vis, which we're going to do a little bit. Okay, now there are 2 terms that get used with molecular orbital theory: highest occupied molecular orbital and lowest unoccupied molecular orbital. That's the HOMO and the LUMO. Okay, now HOMO means highest energy that has electrons in it. We only got one with electrons in it, so that's obviously the one. The other one is lowest unoccupied molecular orbital. Okay, lowest in energy, unoccupied. The more nodes you have, the higher you are in energy. The more bonding interactions you have, the lower you are in energy. Okay, so bonding is when we match. Anti-bonding is when we don't match. That's where the nodes are. You know that? You know that? Okay, so what we'll do is we will do this with 4 pi electrons, 4 p orbitals. Okay, just hang in there. I give it to you very systematically and you'll get it. All right, y'all have a good break. Don't do anything bad. Study, you got homework posted. Did you notice? 2 homework posted. read all those little emails I sent you.